Hello, linear algebra students. We begin the semester by reviewing systems of linear equations. Now, this is a topic that you likely encountered in a college algebra class or saw in some other math class to some extent. We begin with an application. Suppose $378 is the revenue from selling tickets to Friday's school play. Students had to pay $2.50 each, and non-students had to pay $3.50 each. 120 tickets were sold. Use three methods, substitution, elimination, and a graph to find the number of students and the number of non-students who attended the play. So basically, we are going to wind up creating a couple of equations that have a few variables and then solve that system of equations for the variables to resolve this task. Now, the first thing we want to take into account is we need to account for all the tickets. It's 120 tickets, and then we also need to account for all the revenue, $378. And what we don't know is how many tickets of each type that were sold. So we use variables or unknowns to represent these two quantities. It doesn't really matter which letters you pick, but I'll go with X and Y. Let's begin with X representing the number of student tickets, and Y will be the number of non-student tickets. All right, the first equation we must write will account for the total number of tickets. We'll call it the ticket equation. We know that the number of tickets X plus the number of tickets Y should equal 120. Now we are going to write a revenue equation. We know that the amount of revenue brought in from the student tickets will be the number of student tickets times the price per student ticket, which was $2.50. And I'll use 2.5 for that. So 2.5 times X will be the revenue from the student tickets, and 3.5 Y will be the revenue from the non-student tickets, and this should add to our total amount of $378. Now this creates what we call a system of two equations and with two unknowns, X and Y. To solve the system, there are a variety of methods that we've learned in a college algebra class. We're going to use one method called substitution, another method called elimination, and then we'll also use technology to graph the two equations and look for any points they may have in common. So beginning with substitution methods. This is where you take any one of the two equations and solve it for either variable X or Y. It does not matter. There are lots of ways to begin this. I'm going to take the first equation, X plus Y, the ticket equation, and solve it for X or Y. Doing that, I'll solve for Y. We get Y is equal to 120 minus X. Now, once you use one of the equations to isolate a variable, then you substitute that expression into the second equation, into the other equation. And so this leads to, now rewriting the revenue equation, we have 2.5x plus 3.5y, and I'll substitute in for y this 120 minus x, and that equals 378. Now this results in an equation that has only one unknown, x, and we can solve for it. So doing a little bit of algebra here, we have 2.5x plus 3.5 times 120 minus 3.5x equals 378. Combining the x terms, we have negative 1x, really, is what we get here. Negative 1x, so just negative x is good enough, is equal to, and I'm going to subtract the 420 to the other side, and 378 minus 420 is negative 42. And now multiply both sides by negative 1, and we get x has to therefore be 42. And this is the number of student tickets. Now, once we know one of the two unknowns, we can find the other by substituting x equals 42 into either of the equations, the ticket equation or the revenue equation. It doesn't really matter. I'll substitute it, or you can also substitute into this expression right here, which is what I'll do. And we get y, therefore, has to be equal to 120 minus the 42, and that gives us 78 non-student tickets. And we've resolved this task via substitution methods. Now, this would be rather easy to verify that it's a correct solution. First of all, do they add together to be 120? The answer to that question is yes. And then the next question, of course, is does the revenue equation also get satisfied? So 42 tickets times 250, and then plus 78 tickets times 350, and see if, in fact, that does generate $378. I'll leave it to you to verify, but the answer will be yes. So we have the tools to verify that this is in fact a valid solution, and we don't necessarily need to get confirmation from some other source. Another method is known as elimination. Now, elimination is a very useful tool. I actually prefer using it as much as possible. You want to adjust one or both equations in this system of two equations. in such a way that when added together, one of the two variables will cancel each other. Other things that you can do if you don't like working with the decimals is you can convert the decimals to fractions, or you can multiply both sides of the equation by some appropriate number so that the decimals all go away. For example, if I were to double both sides of the bottom equation, it would yield a new bottom equation, which would be 5x plus 7y equals, and then we have to double 378, which will be 756. And so now we can basically take our first equation and group it now with our adjusted second equation, and there are no more fractions or decimals to contend with. Sometimes it's easier to do mental arithmetic when that's the case. Now I still don't have a situation where if I add the equations together, I'll get elimination of a variable. And I'm going to target elimination of the x variables. Now, one coefficient is 5x, or is 5, and the other coefficient is 1. And I want them to be opposites of each other so that when added together, they will cancel. So that means I need to adjust the second equation by multiplying it by -5. And I get to rewrite that second equation. And that produces the following. We get -5x, -5y, so -5y equals, and then -5 times 120 is going to give us a -600. And this is our adjusted first equation. So I'm going to take that with my adjusted second equation and put them together. And I'll leave my adjustment notations up there. So those are the two changes I made to the two equations in order to set them up so that when added together, we get a nice simple cancellation of some variables. Adding the two equations together, the x's eliminate, but the y's will add to a positive 2y. And then the -600 and the positive 756 will add to 156. And then solving for y, divide both sides by 2, and we have our 78. And remember, y was the non-student tickets. And then once we know this one answer, we can find x via substituting y back into either equation and solving for x, and that will confirm that we get x equals 42 student tickets. Now, in order to do the graphing method to confirm that this is in fact the answer, we would reach for some sort of graphing software. I'm going to use Desmos as my graphing software. In Desmos, I'm going to graph both equations. So we had x plus y is equal to 120. Now I'm going to zoom out in Desmos so I can see where the graph actually is. And here's our graph of our linear equation. Now this is a linear equation, so I'm not surprised to see that it produces the shape of a line when graphed in the xy plane. Now the second equation, I'll graph that in line 2. This one was 2.5x plus 3.5y is equal to 378. And this is also a linear equation, hence it produces the graph of a line. And in this case, we are looking for a point xy that satisfies both equations at the same time. In other words, it's got to be on both graphs at the same time. So we're looking for points of intersection. And in Desmos, if you click on either one of these graphs, the red or the blue, it will automatically find where that graph intersects other graphs that are depicted and the x and other points of interest. One that I'm interested in is the point of intersection. And if I tap it, it'll go highlighted and give us the coordinates. And you can see that the point of intersection is at coordinates 42, 78, where 42 was x and 78 was y. And therefore, x represented the number of student tickets, 42 student tickets, and 78 non-student tickets. Now it's interesting, I want you to begin thinking about when you graph two lines in the xy plane like this, what are the possible scenarios as far as points of intersection are concerned? Keep that in mind as we move forward. All right, page 2. Solve each system below using substitution or elimination, then graph each equation in the system and interpret your answer. So I'm going to use just elimination methods on both of these. Currently, it is set up so that I have a fraction and I don't necessarily want that fraction. So if you just want to focus on that first, then it's probably a good idea to go ahead and double the second equation. And that leads to a -2x plus a y is equal to -4. Now my goal was just to eliminate the fractions and then reconsider. So I'm looking now at this first equation and this adjusted second equation, and I want to set up elimination. But notice that if I were to add the two equations together right now, you would in fact cancel not only all the variables, so I get a big 0 on the left, but also I cancel everything on the right. So I get a 0 equals 0 situation. When this happens in the case of two lines, it can be confusing what's going on here. Let's go to a graph of this scenario to see if we can make sense of the answer. Okay, so I typed in both equations, And what I'm seeing here is it appears to be, I don't see two different lines. And so the first equation appears to be this line. The second equation appears to be this line. And when I reveal them both, they appear to be the same line. This is suggesting that if we're looking for points of intersection, or points x, y, that satisfy both equations at the same time, it looks like we're going to have many options, because every single point on the line is in fact a point of intersection, because both lines are the same. We are going to conclude that any point on the line is a point of intersection, is a solution to the system. And if you're graphing this by hand, then I would recommend you take either one of these equations. So let's start with equation 1. And go ahead and solve it for y. Put it in the more familiar slope-intercept form, y equals mx plus b. So we have y equals 2x minus 4. And if you recall from algebra, y equals mx plus b. So the b is negative 4. That's our y-intercept of the line. And the slope is 2. So that means that we would go, you can think of 2 as 2 over 1, rise over run. So a rise of 2 and a run of 1. So if I go right 1, I would go up 2 to get to another point on the curve, or on the line. And therefore, I need to draw a line that passes through these points. So here's a graph of our equation 1. But if you take equation 2 and you were to solve it for y, I'll go ahead and do the original version of equation 2. So I'm going to leave the 1/2 y on the left side of the equation. So looking at equation 2, the original version, so you have 1/2 y equals, I'm going to add x to the other side, so we have x minus 2. And then to get y isolated, I'm going to double both sides. So y equals 2x minus 4. And this is a dead giveaway. When you take both equations and you solve them both for y, and you wind up getting the exact same mx plus b form, this is how you know basically we're working with the exact same line. They were just presented differently as two different equations. So the solution is infinitely many answers. So we're going to say it this way. All points on the line y equals 2x minus 4 form the solution set. Okay, let's take a look at the second example on this page. I just want to set up the elimination. I'm going to, again, target the x's for elimination, which means I really want a positive 3 right here in front of this x, suggesting to us that maybe we should triple the first equation first. So we have 3x plus 6y equals negative 12. This time, when you add the equations together, you get the x's and the y's both cancel, again, like last time. But this time, the constants do not become 0. They become something non-zero, in this case 6. This produces a statement that's just false, which suggests that there's something funny going on with this particular collection of lines. Let's go to Desmos and graph them. Okay, here are the two graphs in Desmos. You can see that they appear to be parallel lines, but let's confirm by hand that these are in fact parallel lines without any points of intersection. If you were to take equation 1 and solve it for y, it would be, I'll get the 2y isolated first by subtracting the x to the other side, so negative x minus 4, and then divide everything by 2. So we have y equals negative 1/2 x minus 2. This is our first equation, so the slope is negative 1/2 and the y-intercept is negative 2. So negative 2 y-intercept and a slope of negative 1/2. I'm going to think of the rise as being negative 1 and the run being 2, so that would be a run 2 and a rise of negative 1, down 1. There would be a second point right there. Whereas equation 2, we have negative 6y is equal to, add 3x to the other side, so 3x plus 18. Now divide everything by negative 6, so we have y equals 3 over negative 6 winds up just being negative 1/2 times x, and then 18 divided by negative 6 is negative 3. So this one winds up producing a line that has the same slope as the first equation, but a different y-intercept. So the fact that we have two lines with the same slope but different y-intercepts suggests that they are in fact parallel, and they will never intersect. They are not the same line. Therefore, there are no points of intersection, and in a case like this, we say that the system is inconsistent or that there's no solution. Okay, let's go to the next page. Fill in any missing entries in the tables below. So we're going to work in 2-dimension, and then we're going to expand up to 3-dimension. When you're working with a linear equation in 2 dimensions, that just simply means that we have two variables. So this first example is a 2-dimensional system. We have two variables, x and y. Now, the equation is linear because x and y are each raised to the 1 power, and they are in separate terms. The a and the b and the c can be any real numbers. However, we don't want a and b to both be 0, because then we would have no variables in the equation. And the geometric shape would be a line in 2-space, or a line in a plane. When I say 2-space, I'm really talking about 2-dimensional space, so that would be like a plane, like the xy plane. Now, if we add an extra variable and create in a linear equation. So x, y, and z all are raised to the 1 power and in separate terms. The number of variables dictates the dimension, so this will be a three-dimensional situation. And a linear equation in 3 variables in 3 dimensions, when you graph it, actually makes the shape of a plane in 3 space. And of course, we don't want a, b, and c to all be 0 at the same time, but some of them can be 0. As stated before, a system with at least one solution is called consistent, and a system with no solution is called inconsistent. Now, given a system of linear equations, there can only be one of 3 cases regarding the solutions. It's easy to visualize why only certain kinds of solution sets are possible. So let's examine the 2-dimensional case in this table below. In the case where there's no solution, this is where we expect in 2 dimensions, we're graphing lines and planes. This is when we have the lines that are parallel, but not the same. So we have parallel lines. There's no solution in a case like this. If there's going to be one solution, then you just need to have ultimately lines that have different slopes. Once you have 2 lines with different slopes, or maybe a vertical line and a non-vertical line, then you have a situation where there would be only one solution. And the other possibility is that there are going to be infinitely many solutions, and this would be a situation where both curves are the same line. So we'll say that this represents both lines. Therefore, any point on that line would be a point of intersection, and there would be infinitely many. Now, it turns out that with linear equations in higher dimensions, that these 3 cases still remain the only 3 possible cases. So here's some imagery we have over here to help us understand in the 3-dimensional cases some of the possible outcomes. So no solution would be, let's pretend we have 3 equations with 3 unknowns, x, y, and z. Equation 1, equation 2, and equation 3 might produce, the red, the green, and the blue planes. And so this here might be the graph of one system. But notice how the planes intersect in such a way that it's true that there are 2 planes that intersect each other in a variety of ways, but there are no points where all 3 planes. To be a solution to a system, you have to satisfy all of the equations in the system. So if you're working with 3 equations and 3 unknowns, then you're looking for points of intersection on all 3 planes, not just on some of them. And so this first case I have circled here, you can see that there's no point common to all 3 planes at the same time. Now you have a similar situation with this middle example, right? Each plane would represent a different equation, so you see the 3 different colors, 3 different equations, but it looks like 2 of the planes, the green and the blue, are parallel and don't ever touch. So it doesn't matter that the red one crosses through both of them. There are no points that could be on all 3 colors at the same time, on all 3 planes. So this would be an inconsistent scenario. And of course, also we have this trivial, obvious case where there's no points of intersection at all, even between any 2 planes, because all 3 of them are parallel. Now, the one solution scenario would be where the planes intersect in such a way that you see one solution. The planes intersect all at that black point in the middle. That would be our one point of intersection. This would have one solution. And then infinitely many solutions can happen a variety of ways. You could have the planes intersecting in such a way that they all intersect along that black line, but none of the planes are the same plane, but they all have a linear set of solutions, if you will. All the points are along a line. It might be the case that you're only working with 2 equations, but 3 unknowns. And so you have, again, the 2 planes intersect in such a way that they intersect along a line. So there would be infinitely many points of intersection. And then here's a situation where this is trying to suggest that all 3 equations 1, 2, and 3, all in the end represented the same plane, in which case every single point on this plane would be a point of intersection. Now, of these 3 cases, the bottom 2 are said to be consistent, and only the first case is considered inconsistent. All right, let's go to the next page. Now we're going to use matrices to help us solve systems of equations. A matrix is simply a rectangular array of objects. We'll talk a lot more about matrices in the next topic, and then, of course, throughout the rest of the semester. Now, systems of linear equations can be solved by converting the system to an augmented matrix, which can then be manipulated to reveal the solution. We're going to convert each system below to an augmented matrix. So on this page, we're just going to do, how do I write these systems of equations as matrices? Now, the first thing you want to do when you're doing this is to order your variables and the equations in the same way. And it really doesn't matter the order in which you choose to go. But normally if there's x and y, we'll put x first, then y second. If there's x, y, and z, we'll just go in alphabetical order. And sometimes extra variables are even added, so like a w. And even though w alphabetically comes before x, it's very common to put w at the end. So like X, Y, Z, and then W. But of course, if you choose, you can pick any order of the variables that you want. You just have to be consistent. So in this first case, we just have two equations, two unknowns. The x's are followed by the y's, and then we have an equal sign, and then we have we call the constants on the other side of the equal sign. So these are called the variable terms because there's a variable attached, and this is called the constant term because there's no variable attached. Everything's already ordered. This is an easy system to convert into a matrix. You simply grab the coefficients of x and y and write them down as numbers side by side, so 3 and 1. And then you next write the constant that's on the other side of the equal sign, which is 4. And you do this for the first equation, and then you do it again for the second equation. So 5, 2, and -1. And then you put some square brackets around this to make it a matrix, a rectangular array of numbers. And then another practice that's commonly done, although not necessary, but is to put a vertical line over here to represent where the equal sign was, suggesting that the 4 and the -1 were on the right side of the equal sign. And this is called an augmented matrix of the system. And we use the word augmented to suggest that it's been expanded. So sometimes some people will say that here's a 2 by 2 matrix, here's a square matrix that represents just the coefficients, and then we augment it by adding this extra column over here that represents the constants. And so that's why we call this an augmented or expanded matrix, to also include the constants involved in the equations. Looking at this next example, I'm not going to get rid of the fractions. I'm just going to convert the equations as they are written into an augmented matrix. But the thing that's going to be important here is we have 3 variables, x, y, z. I also see 3 equations. And what we want to do is make sure the ordering of the x, y's, and z's are all consistent. And you can see that we have some manipulation to do here, because looking at this second equation, x's and y's are backwards here. Also, we have this -4. We have a constant term, but it's on the wrong side of the equal sign, so we're going to have to add that to this 0 side. And the third equation, we got to move the y to join the variable terms, and then add this 2 over to the right side to put the constant on the right side of the equal sign. Now, the first equation is already perfectly ordered. So I'm going to convert the first equation to a row in our matrix. So we have the 1/2 is the coefficient of x, a 1 is the coefficient of y, and a 2 is the coefficient of z. And this is equal to 15/2. Now, we've committed to x, y, z in that order. So looking now at the second equation, the coefficient of x we must write first, which is -1, then the coefficient of y, which is +3, then the coefficient of z, which is -1, and then we have to add the constant -4 to the right side and put a +4 on the other side of the equal sign. And then the third equation, the coefficient of x is 5, the coefficient of y, I'm going to have to subtract the y over, so it's going to be -1. The coefficient of z is 3, and then we're going to have to add the 2 to the other side and put a constant 2 on the other side of the equal sign. So here's my vertical line to represent the equal sign, and then I'll put the square brackets to contain this matrix. Okay, over here, notice we have only 2 equations, but I do notice that I see a total of 4 variables. I see x, y's, z's, and w's. Even though not all 4 variables are present in each equation, the total number of variables in the system is 4. But there are only 2 equations. I'm going to go with the ordering x, y, z, and then w. So looking at the first equation, the coefficient of x is 1, coefficient of y is -1, coefficient of z, there is no z, so you can say there's a 0 coefficient for z, and then the coefficient of w is 2, and then we do the constant on the other side of the equal sign is 9. The second equation, the coefficient of x is 0, I don't see an x. The coefficient of y is 0, because there is no y. The coefficient of z is -1, the coefficient of w is 3, and then we have to move that 8 to the other side of the equal sign, so it'll be a -8. Then we put a vertical line where the equal sign is, and then we square brackets to contain this matrix. And that system has now been converted to an augmented matrix. Okay, let's go to the next slide. A matrix is in row echelon form if it meets the following 3 conditions. We're going to say RE form for short. The first condition, the leading entry or pivot position of each row is a 1. Now, the leading entry or pivot position of a row is simply the first non-zero entry of that row, if there is one. And this pivot position that's a 1, we also call it a leading one. So the leading entries all have to be 1s, basically. Second condition is that the leading ones have to appear further to the right as you go from row to row. So as you go down the rows, you have to see your leading ones further and further to the right. And then number 3, any rows of all zeros are at the bottom of the matrix. So these first 3 conditions, if they're satisfied, the matrix will be in row echelon form. So we're going to scan our 5 examples down here for the first 3 conditions. All right, condition 1. Here we go. Scan this first row. The first non-zero entry in that row is right here. And the question is it a 1? Yes or no? It is a 1. Check. Look at the next row. The first non-zero entry as you go from left to right is this position. So this is our leading entry, and it is also a 1. The third row, we have a problem right here. Here's the leading entry. It's the first non-zero entry, but it is not a 1. So condition 1 is violated. 1, 2, 3 stands for conditions 1, 2, and 3. And we're going to put an X next to this, and I'll use a check mark if it's satisfied and an X if it's not satisfied. Let's just examine condition 1 for all of these matrices. Looking at our second example, the first I'll circle the leading entries. It's a 1. Leading entry here is a 1. Leading entry here is a 1. So that means the first condition is satisfied. Check. Let's look at the next example. We have a leading entry of a 1. Now this matrix has a row of zeros. That means there is no leading entry in it. So not every row has a leading entry because not every row has a non-zero entry somewhere. So we get to condition 1 doesn't apply to this row. But the next row, here's our leading entry, and it is also a 1. So there's only 2 leading entries in this matrix total, and they're both 1s. So that means condition 1 is satisfied. Next example, we have 2 leading entries again, and they're both 1s. Third row has no leading entry, but all the leading entries are 1s. And in the final case, once again, we have 2 leading entries. They're both 1s. So we have condition 1 satisfied. All right, condition 2 was leading 1s have to appear further to the right from row to row. So now we get to look at whether or not condition 2 is satisfied. Now, condition 2, we're not even going to bother really continuing with the first matrix because we're trying to identify whether these matrices are an RE form, and they cannot be an RE form if any of the conditions are not satisfied. We'll just say there's no bother continuing with our assessment. Once you have one condition not satisfied, you can just say the matrix is not in row echelon form. Let's look at this next middle case here. So we have a leading entry here, that's a 1, a leading entry here, that's a 1, and a leading entry here, that's a 1. But as you go down the rows, notice that our leading 1 went from this position, went from the first column to the third column, and then went back to the second column. So it's this relationship here that's actually going to be a violation of condition 2. The leading 1s have to appear further to the right as we go down the matrix. The leading 1 in the third row is further left of the leading 1 in the second row. And that is a violation of condition 2. And we're not even going to bother with checking condition 3 on that matrix. The next one, we have only 2 leading 1s. There's a leading 1 here and a leading 1 here. And so when you look at the relative position, we only went to the right as we went down. So this means that condition 2 is satisfied in this matrix. Next case, again, we see this leading 1s are further to the right as we go down, and that's also going to be the case in our last example. So we have condition 2 satisfied in both of these matrices. Now, condition 3 is any rows of all zeros are at the bottom of the matrix. So condition 3 only applies if there are rows of zeros. Now, we're done analyzing. We're going to say no bother. We just don't bother continuing with our analysis if we find a condition not satisfied. Now, in this first case that we're looking at right here, there is a row of all zeros, and it is not at the bottom of the matrix. So condition 3 is violated. However, for the other 2 matrices, there is a row of 0, and it is at the bottom of the matrix. And if there happen to be more than one row of all zeros, then just make sure they're all at the bottom of the matrix. So in these cases, both condition 3 is satisfied in both of these matrices over here. Okay, so stepping back and looking at this, if you have an X in any of these conditions, then it's not RE form. So I'm going to say RE question mark and just say no. And that's going to be the case for the first 3 matrices. But for the last 2 matrices, the answer is going to be yes. Okay, let's continue to look at what is said up here, reading this portion right here. A matrix is in reduced row echelon form. We'll say RRE if it also meets a 4th condition. And that 4th condition is all other entries in a pivot column. Now, a pivot column is a column with a pivot position in it. And all other entries in a pivot column are 0. So that's referring to, other than the pivot position itself, all the other entries in that column must be 0 in order to satisfy condition 4. Now, to be in reduced row echelon form, it also has to meet the first 3 conditions. So basically, you just have an extra condition. All 4 conditions must be satisfied. to be in RRE form. So the three matrices that were not in RE form, we're not even going to consider because they can't be in RRE form. What I'm trying to say is if you were to look at a Venn diagram, all matrices that are in RE form, we'll say are inside this circle, and RRE form would be a subset. It's a specialized kind of RE form. So if you were to say a matrix is in RRE form, then it's automatically RE form. All right, so only two matrices of these five that were in RE form are the last two. So let's just focus on those and talk about condition 4. So looking at this one, this matrix here, I'm going to highlight the pivot positions. So we had a pivot position and a pivot position. Therefore, there are only two pivot positions in this entire matrix, meaning that there are only two pivot columns. So now we want to draw our focus to all the other entries in those columns. I do not care about column 3 when I'm doing condition 4 here because column 3 does not have a pivot position. So in the first pivot column, we have a leading 1, and then below it we have two entries. They're both 0. So this column satisfies the fourth condition. However, looking at the second column, there are two entries in it other than the pivot position. So we see a non-zero entry in a pivot column, and so this matrix here fails condition 4. So I'll put condition 4. It fails. So the question is this RRE form? The answer will be no. It is RE form, but not RRE form. So we'll call this, matrix 4. I'll say M sub 4, because this is our fourth matrix in our examples. And so we would be able to place matrix 4 in our Venn diagram. Matrix 4 would be in this section. It'd be RE, but not RRE. And let's now look at our fifth matrix. We'll call it M sub 5. M sub 5 also had two leading ones, so two pivot positions, and they are in columns 1 and 2. And if you look at all the other entries in those columns, other than the pivot positions themselves, we see 2 zeros, and we see 0 and 0. Therefore, condition 4 is satisfied here. Again, it does not matter what's happening in column 3. So basically, just find your leading ones and look both above and below them, and they should be entirely zeros all the way above and all the way below in order to also meet condition 4. So we get to say for this matrix, condition 4 is satisfied. And so the question about is it in reduced row echelon form, the answer is going to be a yes. So in our Venn diagram, that would place matrix 4 inside the inner circle, which means that matrix 5 is not only is it in row echelon form, but it is also in reduced row echelon form. So it's in both forms, technically. And then the first three matrices, matrix 1, 2, and 3, let's label them, matrix 1, matrix 2, matrix 3. As far as our Venn diagram is concerned, they would be outside. So all the first three matrices are not in any of the two forms. Okay, let's move to the next page. A row operation on a matrix is any of the following actions. Number 1, multiply all entries in a row by a non-zero constant. Number 2, interchange any two rows. And number 3, replace a row by adding a multiple of another row to it. Use row operations to put the matrix below into two different RE forms and then into our RE form. Note that a matrix may have any number of RE forms, but its RRE form will be unique. That statement, we're not going to prove that statement in this class, but we'll take that as a given, that the RRE form of a matrix is actually a unique representation. Let's go ahead and explore how we might want to do this. So we have a matrix that has 3 rows and 4 columns, and we would like to put this in reduced row echelon form. Basically, our ideal is that if we can get there to be a 1 in the following positions, here, here, and then here, if we can get those to be 1s and then zeros above and below them, then we will have accomplished our goal. Now, the 1s don't have to be in down the diagonal like this. Sometimes a leading 1 might be a little bit further to the right. As long as they go further and further to the right as you go down the rows of the matrix, then that's acceptable. Maybe the leading 1s will wind up being in these positions, and that's acceptable as well. Or maybe there won't even be, maybe there'll only be 2 pivot positions in the end and not 3. All right, so ideally we want to get a 1 right in this position here. And we have 3 different row operations to be able to do this, to try to accomplish this. If there was already a 1 somewhere in this first column, then I would simply do a row interchange. But there is no 1 in that first column, and so we don't have a row interchange as a nice, easy way. We could multiply an entire row by some non-zero constant. So one way to turn this 2 into a 1 is to go ahead and multiply the entire top row by 1/2. However, that's going to make a fraction here and a fraction here. And if you can avoid fractions, then you want to try to come up with a strategy that does so. So we're trying to find some way to use one of these 3 tools here to get a 1 in that upper position. And a very important row operation that we're going to wind up using is this one here, to replace a row by adding a multiple of another row to it. I can see that if I were to multiply row, or this 2 by -1, that would make it -2, and then add it to this 3, that would turn that 3 into a 1. And that would get a 1 somewhere in that first column. So in order to do row operation 3, I'm going to multiply the top row by -1, like temporarily, keep those numbers in my head, and then add them to row 2 in order to change row 2. So I do a notation like this. I put the number that I'm multiplying a row by outside that row, and then a single arrow saying that I'm then adding that result to that row in order to change that row. So I'm only really changing row 2 here. When I multiply row 1 by -1, I'm only doing that temporarily. Another notation system that you commonly see would be something like this. Do the negative of row 1, so negative r sub 1, and add that to row 2, and that produces a new row 2. But I personally like the notation in red. I think it's easy to follow, and it's a little bit faster to write. Now when we do that, we're going to distribute this -1. We're distribute it to all 4 entries in this row, and then add all 4 entries to the respective entries in the row just below it, in row 2. And also keep in mind that I'm going to produce a new matrix here, but that new matrix, it's only row 2 that's going to change. So I'm going to rewrite first, just copy the rows I'm not targeting for change. Now I'll do the mental work to also to create a new second row. And so we take the -1, we multiply it by 2, and make -2, and then add that to 3. And -2 plus 3 is +1, so I put a +1 there. Then I take the -1 and I multiply it by this -1, and that gives a +1, and then add it to the +1 that's directly below it, and that gives you a 2. Then we take this -1 and multiply it by this 2, and that makes a -2, and then add it to the -2 right below it, that makes -4. And then finally we take this -1, multiply it by this 1 to give me -1, and add it to the 4 below it to make a 3. Just like that, I've used the third row operation to perform an operation that, notice it does not introduce any fractions. So I've avoided fractions entering the matrix, at least for as long as possible. Sometimes it's not possible to avoid fractions entirely. And there are lots of ways to use these 3 tools to accomplish our goals. I'm only showing you one approach. It's very possible that 10 different students might do this 10 completely different ways. Okay, now that I have a 1 somewhere in the first column, I will do the row interchange, which is row operation 2. And my notation is simply to do a double-sided arrow pointing at the rows that I'm interchanging. And more formally, you will see notations like this. They'll say row 1 interchange with row 2. Okay, so I'm going to rewrite my new matrix and then interchange rows 1 and 2. Again, what I'm setting up here, so now I have a 1 in the top left position. That's a pivot 1. And we want to get zeros below it right away. And so I'm going to use the third row operation to do this. So I'm going to multiply the top row temporarily by -2, and then add that to the second row. Now when I do this, I'm only targeting for change the second row. So I'm going to copy the matrix and just erase the second row, and that's the one that will be adjusted. Take this -2 that you see right here and distribute it, multiply it to the 1, and then add it to the 2. So we get -2 plus 2, we get a 0. Put that result there. Now continuing this a little more quickly, -2 times 2 is -4, add to -1 is -5. -2 times -4 is 8, and 8 added to 2 is 10. -2 times 3 is -6, add to 1 is -5. It takes us to this stage. At this point, we can sort of say that the first column is finished. Now we want to focus on the next column. It'd be ideal if we can make this entry here be a 1. And so we have basically two tools to make that a 1. If there was, or 3 tools, kind of depends on the matrix. If there was a 1 already in this position, then I would simply do a row interchange of rows 2 and 3, and that would get the 1 where I want it. We can also consider saying, oh, look, if I turn this 3 into a 6 temporarily and then add it to -5, that would make a 1 right there. So one option would be to double row 3, but then add that to row 2. That would get a 1 in that position. So that might be a route you go. But also notice that every single entry in row 2 is a multiple of 5. So if I divide everything by -5, or multiply everything by -1/5, and then the formal notation for this would simply be, hey, do -1/5 times row 2 in order to make a new row 2. All right, so this is the approach I'm going to take, although, as I pointed out, there were options. Okay, only row 2 is being changed by this row operation. 0 times -1/5 stays 0. -5 times -1/5 goes to +1. 10 times -1/5 is -2. And -5 times -1/5 is also +1. Okay, at this point we have pivot 1s right where we want them. I'm going to focus on the second column right here. If I'm going for RE form, then I have to have a 0 below that 1. If I'm going for RRE form, then I got to get a 0 above that 1 as well. Let's focus right now just on getting to RE form. So I'm going to focus on just getting the 3 to become a 0. So I'm going to use the third row operation. Once again, I'm going to use this leading 1 right here to get the 0 down below. So I'm going to multiply the second row temporarily by -3, and then add that to the third row in order to change the third row. Okay, so I've copied the matrix over. I'm going to erase the third row because I'm changing that. And let's write down what our new third row is going to be. So looking down here to do the row operation, we do -3, right? Distribute it to all 4 of these numbers technically, and then add the results down to the row below it. So we have -3 times 0, 0, add to 0, so that'll stay 0. Now we do -3 times 1 and add to 3 makes 0. -3 times -2 is 6, add to 2 makes 8. -3 times 1 is -3, add to 7 makes 4. Okay, so we are at this point now. One option from here is to change this to a 0 if I'm trying to obtain RRE form directly, but the instructions ask me to put this first into just regular RE form and then to take it a little bit further to go to RRE form. So I'm going to follow those instructions and focus on my next pivot position, which in this case would be this location right here. I want that to be a 1. And the only way I can see, the best way I can see to do that right now is simply just to multiply the entire third row by 1/8. So that will make that 8 into a 1, even though it will introduce a fraction in the final position. Like I said, it's not always the case that you can avoid fractions entirely. Now when I do this, the bottom row, the 2 zeros will not be affected, but the 8 times 1/8 will become a 1, and the 4 times 1/8 will be 4/8 or 1/2. And at this point, we are in RE form. Let's call this RE form 1. Notice it satisfies the first 3 conditions. So the first condition was that each leading entry is a 1, and that's the case. The leading entries are all highlighted. The second condition was that the leading entries are further right as you go down the matrix. That's the case. Third condition for RE form is that if there is a row of all zeros, make sure it's at the bottom. Well, that's not the case here. There is no row of all zeros. And so the third condition does not apply, or you can say it's sort of satisfied by default. Therefore, we are in RE form. Okay, now the instructions say to put this into 2 different RE forms and then into RRE form. What I'm actually going to do here is just do a few more row operations to put this ultimately into RRE form. And as I do that, you're actually going to see various RE forms emerge. But the goal now really is to get to RRE form. Now, in order to be in RRE form, we need the entries above the leading ones to also be 0, which currently I was not focused on. So these 3 entries right here represent the entries that are in pivot columns, and they all need to be 0 in order to satisfy the 4th condition. And I'm going to, again, go column by column. So I'm going to focus on this column first, get that fixed, and then I'll focus on the third column last. So the operation I want to do I'm focusing on this 2 right here. I want that to be 0, and I'm going to use this 1 below it to accomplish that with the third row operation. So I'm going to multiply row 2 by -2, temporarily, and then add that back up to row 1 in order to change row 1. So I'm going to erase all of row 1, and now let's go ahead and perform the operation. We do -2 times 0. So we take this -2 right here, multiply it to the 0, and get 0, and then add that up to that 1. And notice that it won't change the 1 to another value, which is actually very good because we didn't want that to change from being a 1. But this row operation does create a 0 above the second leading one. And then continue with the row operation. We have -2 times -2 is 4. And add that to -4, so that puts a 0 there. Oh, that's kind of nice because I wanted a 0 there anyway. And then -2 times 1 is -2, and add it to 3 makes a 1. Now this technically is still in RE form, but it's not yet in RRE form. So we could say that this is our second case, our second example of being in RE form, because it satisfies the first 3 conditions still, but it doesn't entirely satisfy the 4th condition, because I do see a non-zero entry in a pivot column that needs to be addressed still. So this is where my focus shifts. So I'm going to use the third row operation again. I'm going to use the pivot 1 that's below that -2, so this pivot 1, which is in the third row, multiply the third row by +2 temporarily, right, and add it to the second row to change the second row. Okay, so we are trying to change the second row, so I'm going to erase the entire second row, and let's see what the new second row becomes. So we do 2, this 2 gets to multiply all the way to the 0 and add to 0. Then it's going to multiply to 0 and add to 1, and multiply here, add to there, multiply here, and add to there. So make sure you do all 4 steps. So 2 times 0, add to 0, stays 0, which is actually good. I didn't want that to become something else. 2 times 0 is 0, add to 1. That stays a 1, which is also good because that was a pivot position. We did not want that to be a non-1. And then 2 times 1 is 2, add to -2 makes a 0 there. And 2 times 1/2 is 1, and add to 1 puts a 2 right here. Okay, so this now, after this row operation, is now in RRE form. Now, there are many possible different RE forms of a matrix. But if you're going for RRE form, by the time you get there, then you will have a unique representation, which means that no matter which approach you took here, these numbers over here would not be any different than what you're seeing. The RRE form is unique. Okay, let's go to the next page. Gaussian elimination and Gauss-Jordan elimination are 2 subtly distinct methods for solving a system of linear equations. Consider the schematic below. Okay, so we're starting to put all the pieces together. If you begin with a system of linear equations and then you convert it to an augmented matrix, we practiced that. And then if you use row operations to obtain RE form, and then from there, you convert back the reduced matrix back to equations, and then you determine the solution. So basically, if you go this upper route here, this is one approach you can use to use matrices as a tool for solving systems of equations. As another option is you can sort of go this lower route, which is where you continue with the row operations until the matrix is in RRE form. In general, it'll be better to put the matrix in RRE form before you convert the augmented matrix back into a system. But you do have options. And in fact, at any point along the process of doing row operations, you could, in theory, go back to your system of equations and continue to analyze the system from there. Now, if you do the upper route, this is the one that is referred to as Gaussian elimination. Gauss was a mathematician. However, if you were to go the lower route is the one that's referred to as Gauss-Jordan elimination. In general, if you're going to default to one of these 2 methods, I recommend that you default to Gauss-Jordan, that you continue with the row operations until the matrix is in its unique RRE form, and then you interpret your solutions from that form. The more zeros you have in your augmented matrix, the easier it will be to interpret the meaning of your solutions. All right, solve the system below using each method. Okay, so we have a system, 3 equations, 3 unknowns. So the first equation becomes, we have a 2, a -1, a 2, an equal sign, and then a 1. And we didn't have to do any unscrambling. But the second equation, I see the y and z are backwards. So just be mindful, the coefficient of x must be in the first column. So we have 3, then the coefficient of y, which is 1, then the coefficient of z, -2, and then the equal sign and the constant, which is 4. And in the last equation, notice there is no x, so we do have a 0 to begin. The y coefficient is 3, the z coefficient is 2, and we do have to add that 7 to the other side. And just like that, we've created our augmented matrix. I'll put the vertical line to represent the equal sign. Now we have to use row operations to put this matrix in reduced row echelon form or row echelon form. We've been asked to demonstrate both methods. So you'll notice, though, if you go back a slide, that this is the exact same matrix that we already been working with. So I'm not going to have to duplicate all these steps. We've done them once. And so let's pick one of our row echelon forms. In fact, let's pick the first row echelon form we obtained. And this is a row echelon form. And then from there, we're going to convert this back into equations. So we have the first row. We have 1x, we have 2y's, so plus 2y. We have minus 4z is equal, and the equal sign, then we have the 3. The second row would read no x's, but 1y. So 1y minus 2z. Notice I'm crossing my z's. That's a good habit to have. If you don't cross your z's, they look too much like 2's and you'll make mistakes. Equals 1. And then the final row actually it gives us a lot of useful information, because the final row would read 0 x's, 0 y's, and 1 z is equal to 1/2. This gives us the solution for z right away. But what's convenient is that now that I know z, I can go backwards to the line above and determine what y is going to have to be. We're doing back substitutions. So if z is 1/2, and then I know that y minus 2z, z is 1/2, has to be equal to 1. So 2 times 1/2 is 1. So y minus 1 equals 1, so y has to be 2. And now that I know what y and z have to be, I can go back to the top equation and plug them in for y and z and solve for x. All right, so this would give us x plus 2y, so 2 times 2, minus 4 times z, and z was 1/2, and that has to be equal to 3. Well, this would be x plus 4 minus 2 is equal to 3. And so this is going to ultimately tell us that x has to be 1. And so we have our solution, z, y, and x. This is the case where we have a unique solution. This is a single point of intersection. I refer you back to our imagery up here. It's a case like this case right here, a single point of intersection for all 3 planes involved. The other approach is to continue with row operations until you're in reduced row echelon form. And in this case here, reduced row echelon form was this bottom form right here. So let me just copy that and paste it down here. And now let's convert the rows back into equations from this form. And you'll notice something very useful right away. We do have that equal sign represented right there. So the first row would read 1x, so just x, no y's and no z's, equals, and 1. The second row would read no x but 1y, no z is equal to 2. And the third row would read only z is equal to 1/2. So notice when my reduced row echelon form, I get my answer just from the last column, basically. The last column tells me what x, y, and z have to be, and we have our solution right away. So once again, if you're doing Gaussian elimination, you're basically going this route to get your answer. And if you're doing Gauss-Jordan elimination, you're basically going this route to get your answer. The next slide. Gauss-Jordan elimination is especially helpful in describing solutions for those cases where there are infinitely many solutions. Give the solutions, if any, to each corresponding system of equations. So we have 4 different augmented matrices corresponding to a system of equations, and we need to put them in reduced row echelon form and then interpret an answer from that. I'll show you how to do this. Focusing on our first matrix, I'm going to go ahead and put that vertical line in there that represents the equal sign. And there's already, these matrices, it won't require very many row operations to get to reduced row echelon form. They're already pretty close. For example, this already has a leading one here and a leading one here. We've already got these zeros below, and there's already a 0 above this one. So I really just want to focus on making this one a 0 next. So I'm going to multiply row 2 by -2 and add that to row 3, and let's see what that produces for us. So -2 times 0, add to 0, stays 0. Negative 2 times 1 is negative 2. Add to 2 becomes 0. Negative 2 times negative 1 is 2. Add that to negative 2 becomes 0. And then negative 2 times 0 and add to 3, this will stay a 3. I see 3 leading positions, 3 pivot positions. The last one's not a 1 yet, so technically this is not yet in RE form because we need a 1 in that last position. However, I know that I can stop the process right now as far as interpreting solutions because the very last row is all zeros, an equal sign, and then a non-zero. The very last row, so we'll say row 3, tells us that 0x plus 0y plus 0z, so in other words 0, has to be equal to 3, which is, of course, is a false statement. When this kind of thing happens, then we have an inconsistent system. Again, when this phenomenon happens, you don't need to bother continuing the row operations to get to row echelon or reduced row echelon form. You can recognize the difficulty as soon as it occurs and say inconsistent and move on. Second case, let's put our equal sign here. I see we have a row of zeros that's at the bottom. I do have my leading entries descending in the correct pattern, but this one here is not a 1. So I want that to be a 1, and I think if I just multiply that row by 1/2, that will be appropriate. Notice row 3, if you were to convert it to an equation, would read 0 equals 0, which is not a contradiction. This satisfies all 4 conditions right now, right away, so this is RRE form. And we're going to interpret the solutions from this. There's going to be infinitely many solutions in this case. So we have x, y, and z. So row 1 is going to read x, no y, minus 5z is equal to 2. The second row is going to read y, minus z is equal to 0. And the third row, don't bother converting it. It's useless information. It just says 0 equals 0. The leading ones are only in the x and y columns. Notice the z column has no leading 1. It might have a 1 somewhere in there, but it's not a leading 1. The only leading ones in this matrix are the 2 orange highlighted ones. So the z column is missing a leading 1. When that occurs, we get to say that z is free. Z is going to be a free variable. It can be anything it wants, which means that the other 2 equations that you wrote down, solve them for the non-free variables. So x and y are non-free. So solving them for x and y respectively, we get x has to be 2 plus 5z. We're going to cross your z's, otherwise that looks like 52. And y has to be equal to just z. And z is free. So our solution, normally we present our solution as x, y, z. And in the case where we have a unique solution, these would all 3 be numbers. But in this case here, we have a free variable, a variable that can be anything it wants, and that's z. But the other 2 variables are dependent on z. They are not free variables. We call them basic variables. So all the variables in the equation will either be free or basic. In this case, x and y are basic, and z is free. So the ones that are basic, x and y, which are dependent on z, you replace them with the equations you got above, that x has to be 2 plus 5z, y has to just be z, and z is free, so z can be whatever it wants. So your answers are infinitely many, where z is any real. If you remember, real symbol for real is the bold R, like that, bold capital R, any real number. And this is our solution set. So you would basically, if you want a specific point, that's a point of intersection, you pick z first, and then z then will dictate what the other 2 coordinates have to be. So if z was 10, for example, then one point would be 52, 10, 10. Free variables always lead to infinitely many solutions. All right, next case. We have leading ones. We have a row of zeros at the bottom. And so right now, condition 4 is not satisfied because this entry here, it's not a 0. So I'm going to multiply row 2 by -1 temporarily and add that up to row 1 to change row 1. And now we are in RRE form. Now let's convert back to equations. This time, you'll notice that it's we have the x, y, and z columns, respectively. This time it's the y column is the column that doesn't have a leading entry in it. There's no leading 1 in the y column, so it's y that's going to be free. And let's go ahead and translate row 1 into an equation. It reads x plus 2y, no z, is equal to 2. And row 2 would just becomes z is equal to 4. And we have y is free. So our answer is going to be the following. We take this first equation, solve it for x. X is a basic variable, and so is z. x is equal to 2 minus 2y. So y is free, and x is dependent on y. Z is independent of y, but x and z, we call them both basic variables. And our solution set will be the x, so we have 2 minus 2y. We have y is free, so y is just y, and then z has to be 4. And this is how I would describe my solution set, where y is an element of the real numbers. Okay, one last case here. Let's go ahead and throw our equal sign in there. We are not in reduced row echelon form yet. We do have a leading one right here, but we need a 0 below that, so I'm going to focus on that by multiplying row 1 by -2 temporarily and adding that to row 2 to change row 2. So this is in reduced row echelon form. This time it is column y and column z are both missing leading ones. And so this is a case where we have two free variables. So the first row reads x plus 2y plus 4z is equal to -1. Solve this for x. We get x has to therefore be -2y minus 4z, and then that -1 still there. And then our solution has the form x, y, z, and y and z are both free. So we put this expression in the x position of our answer, comma, y is free, so y just stays y, and z is free, z stays z. And then we say y is free, so y can be any real number, and z is free, so z can be any real number. And they're not dependent on each other. You can pick y to be 10 and then z to be -7. You just pick whatever two numbers you want for y and z, but once you pick them, then you plug them into this relationship right here to then say what x has to be. So x is dependent on both choices. Now you'll notice that here we saw sort of a full spectrum of possibilities regarding three-dimensional equations, because we just had three variables x, y, and z in each case, and therefore we're analyzing how planes are interacting with each other. Now in the first case, we had the inconsistent. There was no point of intersection common to all three planes. In the middle two cases, we had one free variable each. So there's one free variable in each of these. And in the final case, we had two free variables. Now, just so you know what's going on visually in these cases, let's go back up to our images of how planes could possibly interact. When there's one free variable, then your solution set depends on just the one parameter, one free variable, and your solution set is all points along a line. And so we're looking at cases like these two cases, because these ones have points of intersection that follow that black line that you see. And this corresponds to a one free variable scenario. When you have two free variables, then all of your points are along a plane. So you have a situation like this, where all the equations wind up being the same plane. Okay, and then this is an old draft of the guided notes. I've eliminated this sentence here because I want to introduce the idea of rank a little bit later in class. So this sentence I've just eliminated from the current guided notes. And that wraps up our discussion on systems of linear equations and how to use matrices to solve them.